I'd like to now introduce Margie Ackerman, who's a professor of engineering, and her work focuses on the correlates of protection from infectious diseases, including HIV and TB. Our TB vaccine group's been very fortunate to collaborate with her. She might be described as the ultimate collaborator. Many, many collaborations. Margie.
Thank you, Ford. Okay. So I had this ambitious goal of telling you all about how bigger data, smaller trials, and new approaches could facilitate vaccine development for tough pathogens. We've heard a lot of success stories today, but there are many diseases which we would like to have vaccines for that we don't as of yet. And I was perhaps overambitious. I'm not going to get as far into smaller trials as I would have liked, but was happy to see Phil present kind of that adaptive trial design. I think there's also pushes towards experimental medicine trials in the vaccine space as well that will help us make faster progress or more meaningful progress towards some of these really tough pathogens. And perhaps one of the ones that has already figured prominently in today is HIV. And so if we look at efficacy trials over the last 20 years for HIV, it's really pretty clinically depressing, right? So we have a lot of failures, things that have failed to meet their endpoint efficacy criteria. We had that one glimmer of hope, the RB144 trial that Patricia already mentioned earlier today, that showed a modest level of efficacy that didn't look terribly durable, but was the first positive signal in a major efficacy trial. Even broadly neutralizing antibody as an intervention to prevent infection. You see on the top half of the graph, the HVTN 703 or 704 AMP trials failed to meet their overall efficacy criteria. So this is a big and challenging problem. Nothing like the super fun work David described where everything works and helps keep me from being clinically depressed. And nothing like, fortunately, what the world experienced with COVID, where in a matter of 2 years, we had 4 vaccines in the US, more globally, and 5 monoclonal antibody products that have been used at different points in time and continued development, and we anticipate continued success. All right, so why is HIV so challenging? And some of these attributes are things that are in common with other vaccine recalcitrant pathogens like TB. So here, natural immunity kind of doesn't exist. So you can be infected with HIV, and that response to the virus is so ineffective that you can be infected with another strain or super infected with a relative of the strain that you already have, a different clade or whatnot. Lifelong infection is established like HSV. This is a virus that goes latent as part of its life cycle. And it's really rare for infected individuals to be able to spontaneously suppress viremia. So the immune system, this is one bug that has really found some clever ways to evade our immune system's capacity to combat it. The other point I wanted to make is that the virus is incredibly diverse. So we've seen some of these, we saw the diagram for coronaviruses, alpha, beta, et cetera, coronaviruses. Here you have SARS-CoV-2 represented as that dot indicated at the end of that red arrow. That's diversity in SARS-CoV-2 compared to, on the same scale, HIV-1 across clades. And so if we think about what's happened with variants in the context of COVID, imagine the challenge that awaits us with a virus that's this polymorphic, right? And people like to use the handy saying that, there's greater viral diversity in a single HIV-infected subject than experienced globally in a year's worth of influenza cases. So this is a really, really tough problem. And another challenge, I'll posit to you today, is that we've had relatively few trials and limited opportunities to relate natural immune responses to outcomes. We've really struggled to have beneficial outcomes, and so understanding how attributes of the immune response might relate to resistance to infection has been challenging. All right, but we had that one little hint of a vaccine that may have protected some subjects against some viruses, and the question is, how? And so the way that it's traditionally undertaken to understand correlates of protection, which are important waypoints in vaccine licensure, in development of other interventions that might use the same mechanisms of action, is to prioritize and bottleneck a limited number or evaluate a limited number of responses induced by the vaccine so that you maximize statistical power to discover correlates of protection. And so for the RV144 trial, there were 6 primary variables that were selected. So many labs contributed assays. They tried to pick assays that would represent different mechanisms or aspects of the immune response and that were not highly correlated with each other. So they'd get as much kind of discovery power out of those 6 correlates as well. And it was really great. Some of these 6 selected assays related to infection risk, but they really weren't the expected ones, and they weren't always in the expected direction. So there were some aspects of the immune response that were elevated in people who were more likely to become infected than those who were not infected. So this sort of meant that we maybe knew less than we thought we did about what it would take to achieve vaccine-mediated protection from HIV. And so some of those surprises were really that antibodies recognizing what we would think of as perhaps the least attractive or viable part of the virus for a vaccine were those that were correlated with protection, and those were in the hypervariable loops, not the common, consistent kind of, pan-pathogen epitopes that Jason's talk highlighted for coronaviruses and flu this morning. But there was also virologic evidence that these epitopes may have been important, responses to these epitopes may have been important. So in subjects who went on to be infected by virus, the sequences of the viruses were different in placebo recipients from vaccinated individuals. So we've got both immune responses, host and pathogen responses that suggest this might be a real signal, and that some of the vaccine recipients were likely protected from some viruses by this vaccine. But we'd like to learn more, right? We picked 6 measures and 2 of them related to outcome. What if we'd picked 12? Would we have had 4 related to the outcome? Would we have had more? What other insights are we leaving on the table by adopting this kind of statistically principled and rigorous approach to evaluating outcomes in these trials? And this was when my lab started at Dartmouth, so we were sort of confronted with a surprising result from RV144, and we thought we know less than we think we do. Let's just start measuring more. And so the first grad students in the group really developed the system serology platform to make as many measurements as we could conceive of, specifically about the antibody responses that were raised in response to infection or vaccination. And I'll give an example of what those profiles look like. So this is 200 HIV-infected subjects shown on the y-axis, and 200, 500 antibody response attributes shown on the x-axis. And what you can see is that people look pretty different. So we have some people that have high responses with some characteristics and some people that have low responses. I'll call attention to these 2 subjects who had really striking IgG4 responses. So this is a really, really rare response in natural infection, but some of the vaccines we've evaluated for HIV have induced 100% of vaccine recipients to produce IgG4s. That's something that natural infection never does. It's probably not a great thing that we'd like to happen, but it's kind of inspiring from the perspective of vaccines can do things that pathogens don't inherently do themselves. All right, so that generates a lot of data that we'd like to integrate and feed into better understanding of basic immunological processes. And so I'll start with one example of applying this kind of broad profiling approach, so an unbiased on the data input end. And that was for a vaccine that's also been mentioned already today. So the DAR-DAR trial conducted collaboratively between Ford's team here at Dartmouth and in Tanzania. And so this was a vaccine evaluated in HIV-infected adults that was comprised of an M-Abuens vaccine. And it showed 40% efficacy in this population. And so one of the students in our lab undertook a case control study. So the typical design for discovering correlates, you compare recipients of the vaccine who became infected and recipients of the vaccine who were not infected at the end of the trial. We made as many measurements. I wish we could say we were really smart and thoughtful. We just grabbed whatever we could access through repositories and measured as much as we could. And that was about 200 different attributes of the antibody response to this vaccine. And what's shown on the right is what's called a volcano plot that really compares the two populations, those vaccine recipients who were infected. Responses that were higher in that group are shown on the left-hand side of that graph. Responses that were higher in uninfected vaccine recipients are shown on the right-hand side. And what you can see is that there are antibody correlates of vaccine-mediated protection in this trial. This was one where it's a mystery how this worked. There haven't been reported correlates to date, but now we have a start to understand and maybe appreciate the value of antibodies either mechanistically or as a marker of vaccine take and prevention of disease. So that was data kind of shown in isolation, each measurement as its own independent variable, but data can be much stronger and more useful when aggregated. And measurements that have individually small relationships with outcomes, that strength can be amplified when we understand better how responses are related to each other and how the responses in different subjects relate. And we can also start to use machine learning tools to relate what we observe and to make predictions so that we would be able to understand or predict the efficacy of vaccines. And so sometimes I give an analogy, which is this is kind of like Netflix for immunology. So the same way that Netflix uses the viewing patterns of other individuals to make predictions and recommend to you programs that you would enjoy watching, we're trying to do the same thing in the context of natural immune responses, make a lot of measurements, understand how they relate to outcomes against infectious disease challenge, and use those as predictions for the type of response that's desirable. So here's an example of some of this kind of data-driven discovery. This is work that Andrew Hederman did in the lab looking at antibody responses to CMV infection and comparing primary and non-primary infection. And what's shown here will be super familiar to people who work with flow cytometry data, but it's a way to collapse high dimensionality data down into two axes, which is like what our eyeballs are capable of interpreting. And what you can see here in this unsupervised analysis, which really just lets the data structure itself, is that antibodies are super different in non-primary infection than they are in primary infection, but not so different between pregnant individuals and non-pregnant individuals, shown in the symbols. Okay. Something else we can do is to actually build predictive models. So rather than letting the data structure itself, which is great when there's a strong influence across the global data set that relates to your outcome of interest, like it was previously, is to try to dig in and say what specific individual features that we've measured provide what kind of predictive value to the outcome. And so in this data set, we had a number of measurements made. Again, I'm comparing primary and non-primary infection. And we can use, the same tools Netflix is using and take a subset of our data and train a model that we then predict and apply to the held out examples. So these really are predictions rather than fit data models. And it's a different way of looking at data as compared to bottlenecking your analysis on the front end in feature space, but using all of your subjects. Here we're using as many features as possible, but having some statistical robustness by doing that analysis on only a subset of the subjects and applying it to those that the model has never seen. And so when we do that in both the held out data and independent validation cohorts, we can really start to see that, I might watch that program that Netflix recommends to me, right? You can learn patterns that are generalizable across individuals and relate to outcomes. Right. So I won't do too much in terms of under the hood, but suffice it to say, we've done a lot of due diligence to make sure that these are not overfit, exaggerated, that they've supported known biology. We see things we expect to see. And we've also seen new things that we've been able to go back and experimentally validate. All right. So what about the rest of these trials? So a number of the others have also had case control frameworks done. So HVTN 505 is not an HIV vaccine trial that met its overall efficacy endpoint criteria, but you can see differences in the immune response between people who went on to be infected with HIV and those who did not. Same thing for the antibody trials. And so some of those insights afforded, even in the context of an overall ineffective vaccine regimen, were that IgG3 type antibodies and antibodies binding the variable loops of HIV are associated with reduced risk of infection. Similarly, in the AMP trials, adequate levels of antibody in serum and challenge or exposure to neutralization sensitive viruses were endpoints that we could observe and related to infection risk. So this is exciting too. It means we can learn more from our failures, which is mostly what we've done. So that's important. One other thing, pushing the envelope even further, is that when we do these case control designs, we're comparing infected from uninfected subjects. But for vaccines that are poorly effective, most of the uninfected subjects, we expect them to have the same exact profile as the infected subjects, and they're only not infected because they were never exposed. And so they don't really contribute any signal to our analysis. They do contribute a bunch of noise and reduce our power to discover correlates of protection. But this is what's typical. What we'd really like to do is be able to discriminate among the uninfected subjects and make some inferences about which subjects were protected and which subjects were unprotected, because that's really what we care about. We don't care about markers of risk of exposure. We care about markers of risk of infection following exposure. And so in work that Sophie and Natasha did, we investigated a suite of tools called positive unlabeled machine learning, which are really this kind of setting in which you have a definitive label for one group, the infected subjects, and no label for the uninfected subjects. We don't know what the outcome, what their degree of resistance to infection would be. And we're using the same kinds of machine learning tools to really try to discriminate between those two populations. And if we're able to do that, the hope is then that we'll have even more power to discover novel correlates of protection. And so here's an example, sorry, the colors are not quite right here, of, again, a dimensionality reduction of real responses, immunogenicity data from a vaccine efficacy trial. And you can see colored in yellow the response profiles of subjects that were infected, and in purple, those that were uninfected. And if we apply machine learning to make predictions about all of the subjects across this study, for the uninfected subjects, we're able to produce or infer a risk score as to their resistance to infection had they been challenged. And so this gives us a way to hunt for, or we've called it mine the graveyard of failed vaccines to try to gather more insights and new correlates. All right, so there was a little bit of false advertising in terms of experimental medicine studies, but I wanted to thank all the contributors to this work, which include Jason and one of his graduate students who were kind enough to share some protein with us for the CMV studies that I described. Thanks.